This video is going to help us kind of take another direction with power series. So in class, we talked about radius of convergence and interval of convergence for power series, but now we're going to talk about other things that we can do with power series. So we're going to take sort of a new viewpoint. And that new viewpoint idea is the following. We're going to start with a function, and then we're going to make a power series out of that function. So, first we'll make a note that all polynomials are their own power series. They just don't necessarily have an infinite number of non-zero terms. But they still are power series. So something like x squared plus 5x plus 9 is a power series, and it is its own power series representation because there is no other way to write x squared plus 7x or 5x plus 9. The thing we're going to use right now to kind of get us going is to remember the geometric series. So if we remember the geometric series, this guy right here, x to the n, we remember that this converges if the absolute value of x is less than 1. And it converges, remember there was that formula, to a over 1 minus r, and in this case r is x. So that's 1 over 1 minus x. So we are going to talk about the fact this is the kind of big idea we're going to use in the first few examples we're going to talk about how to take 1 over 1 minus x and convert it, or convert something like it, to other interesting looking power series. So the examples that we're going to have are to derive power series for the following functions. So the first one we're going to look at is 1 over 1 plus x. And 1 over 1 plus x, if you look, is pretty close to 1 over 1 minus x. Our goal is to take this one that we know something about and try to convert it. So really this is 1 over 1 minus a negative x. And so if we were looking at this as a function, instead of having an x there, we're going to plug in negative x, because that's the only difference between 1 plus x and 1 minus x. So in other words, the power series representation for 1 over 1 plus x is really the sum n equals 0 to infinity of negative 1 to the n, x to the n. So this is the idea, is that we're taking a function, such as 1 over 1 plus x, and trying to come up with a way to write it as a power series. And so the one that we're using as a sort of baseline is 1 over 1 minus x, and we know that it's equal to x to the n using the geometric series. And then 1 over 1 plus x is just some slightly altered version of 1 over 1 minus x. And so the idea is, I'm just using 1 over 1 minus x, but I've plugged in negative x instead of plugging in x. So where there was an x here, where there was an x down here in the denominator, there's also an x here. So it's pretty much like whatever you change there, you change over here. So we have some further examples. Let's try another one. This is letter B in the example. So if we have x over x plus 1, we can write that as x times 1 over 1 minus a negative x. So that's x times the sum, n equals 0 to infinity, of negative 1 to the n, x to the n from the previous question. And then if you wanted to rewrite that as a single sum, you can take that x on the inside, negative 1 to the n, x to the n plus 1, right? Adding your exponents. So this x and this x combine to give you n plus 1. So that's the idea there. Letter C is 1 over 3 plus x squared, and so this is the one that's probably the most complicated. And the idea here is that the first thing we need is a 1, right? Because that's what we know about, is something about 1 over 1 plus x. So instead of this 3, we need a 1 there. So I'm going to take and multiply the top by 1/3 and the bottom by 1/3. And then if I simplify that, I'm going to have a 1/3 times 1 over 1 plus x squared over 3. And then we can rewrite that as 1/3 times 1 over 1 minus a negative x squared over 3. So now you have a pretty good sense that we have 1 over 1 minus something. So we'll have the 1/3. We'll take our sum, n equals 0 to infinity. And instead of x, this is what we're going to plug in for x, because it's normally 1 minus x. We're going to plug in negative x squared over 3, all raised to the n. And so simplifying that, we get 1/3 the sum, n equals 0 to infinity, of negative 1 to the n, x to the 2n over 3 to the n. And if we want to write it as one single sum, which is usually your goal, we will write it as one single sum. So we'll take the 1/3 inside, and so we'll get the sum n equals 0 to infinity, negative 1 to the n, x to the 2n, and we have a total of 3, n plus 1 in the denominator. And so this is a way to write this function, 1 over 3 plus x squared, as a series, as a power series in particular. So you may be wondering maybe what we would use this idea for. Why would we want to convert a function to something that looks much more complicated? And that's actually what comes in sort of next, is to start thinking about the calculus maybe that we could do on things like this that could be maybe really informative or helpful. So there is a theorem here. So there's a theorem that says if the power series, the sum of an x minus c to the n has radius of convergence r greater than 0, then the function defined by f of x equals the sum, n equals 0 to infinity, of an x minus c to the n is differentiable on c minus r to c plus r. And we can do two things with that function. The first thing is we can take its derivative. So the derivative of this function is exactly what you think it should be if we're taking the derivative of power functions. You can go from n equals 0 to infinity of n a to the n x minus c to the n minus 1. So we just took our function over here. The derivative of a power series, power function, is to take down your exponent, there's your n, and subtract 1 from the exponent. And that's exactly what we did in order to take the derivative. And those are really easy derivatives to take. And so that's why maybe it's sometimes nicer to have a function written as a power series than as maybe a really funky sort of rational function or transcendental function. This is just a really nice power series where taking derivatives is really easy. One thing you can note here is that since we're taking down the n, if n starts at 0, this really becomes like a 0 times stuff. And you may even not even want that 0 there because you don't want stuff raised to the negative 1 and have potential of having a zeros in the denominator. So sometimes we even actually say this is really just equal to starting at 1 raised to the infinity n times a to the n x minus c to the n minus 1. So that's the first concept, and then the second one is that we can actually integrate functions as well that have this power series representation, and you can think about them in a similar way. So if we were going to integrate a power function, remember we add 1 to the exponent, so it becomes x minus c to the n plus 1, and then we divide by that new exponent, and then we'll say this whole thing is plus a, where a is some constant. And one thing is to note in this theorem, the radii of convergence of both of these power series is the same as the original series. So when you take the derivative or when you integrate, you're still going to have this same radius of convergence. One other thing to quickly notice is that you can also substitute a function of x, and that will yield a new power series with possibly a different radius of convergence. So in our examples, when we plugged things in like minus x or plus x squared, and we were sort of plugging in something other than x, the radius there could change. So taking derivatives and integrate doesn't change your radius, but if you plug in a new function, then your radius certainly could change in those situations. So I have two more examples that I will likely work in another video. So if you want to see a couple more examples of how to do power series representations of functions, feel free to watch the next video as well.